Hi again. Okay, so we're at this continuing discussing complete markets economies in the tradition of Aaron de Breu, a bunch of specializations. Markets meet once at time zero. Every commodity in sight is exchanged. Each consumer is a price taker. Consumer maximizes his or her utility functional by choosing a consumption plan subject to subject to Dagger, and Dagger is our Aaron de Breu budget constraint. There's only one budget constraint for each person, obviously. And where we left this is we formed a Lagrangian for the consumer's problem. And we get some tasks for ourselves. We're going to get the first order necessary conditions. That's kind of ingenuous. We're going to stare at them. Then we're going to take ratios of the first order condition for person I to person 1, and we're going to stare at those, and we're going to ask, do they remind you of anything? That's the agenda. Okay, so let's start doing it. So we'll take partial derivative of the functional u I of this whole process. That's shorthand notation for that double sum with respect to CT I ST, consumption at a particular date and a particular history, and we'll get this. We'll get mu I personized Lagrangian times the price. Beautiful formula. Where we'll just remember this object is beta to the t. It's the same thing that we had before, ui prime, just to remind ourselves of CTI S superscript t, the history, times the probability. So that's the marginal utility times the probability times the discount factor raised to the time. So now that means that we get this. Our marginal condition could be rewritten ui prime CT I ST times the probability. Okay, and that's equal to mu I QT 0 of superscript t. That's an I. So there's our Lagrange multiplier times the price, and here's our marginal utility. And then, okay, so that's a first order condition. Now, what we're going to do is we're going to do the division that we recommended. So if we take ui prime CTI of ST, if we take this condition for person I and for person J and divide it, some common things divide out. Evidently equals mu I over mu J. So how did we get that? What divides out? This divides out and this divides out. That depends on pi t and st and beta do not depend on I. Why? Because we assume they didn't. We restricted people's preferences to be the same, except for u sub I does not equal u sub j, possibly, for I not equal to j. We allowed them to have different little one-period utility functions. Otherwise, they would have divided out in a certain way that we'll come back to. Okay. So we got this. This is pretty important, and that reminds me of something that we'll come back to. Okay, so now we need we're going to need some definitions. So we need a definition of a price system. And an allocation. Allocation. So what's a price system? Price system is a it's one of these for all t, for all st. It's a whole sequence. So the price system is a price for every date and every history. An allocation is a CI for I equals 1 through I for everybody. Those are definitions. And now here's a key definition. It's good to keep this in mind. A competitive equilibrium. That's what we're defining. It's good to remind yourself of these. So a competitive equilibrium is going to be is some stuff. So if we went to the stationery store and we got a book of you know, a notebook, there might be one that says some stuff that satisfies some conditions. Couldn't probably see this, so some conditions. Okay, so what's a competitive equilibrium? It's I'll just fill this in, is a feasible allocation and a price system. So that's the stuff that satisfies some, what's the condition? Well, I'll say such that given the price system, so my people are price takers, given the price system, the allocation solves each agent's, each consumer's optimization problem. Okay, that's what a competitive equilibrium is. So now we want to find some and discuss them. Okay, now so So one thing we know is we can use the same trick that we used before, because this is the same equation except that we had before, except instead of being ratios of marginal utilities, I'm sorry, instead of being ratios of Lagrange multipliers on budget constraints, we had, when we studied a planning problem, this has the same form. I'll put this in some black color. This is the same form as an implication of planning problem, where I'm going to get this upside down, where the mu i's were either the Lagrange multipliers or the reciprocals of those Lagrange Pareto weights. So there's a link between Pareto weights. So we have this kind of table. We have Pareto weights. Those were the lambdas. And we have the competitive equilibrium. We have these mu i's. And these things are related. So I want you to fill in this table to tell me exactly how they're related. They're functions of, if they're related in a certain way, then that equation is satisfied for both. So what that means is we can use the same logic that we did earlier, and we can compute CTI of ST. We can, it's exactly the same logic and the same equations. Remember when we did this for the planning problem? U1 prime CT1 of ST. And then instead of, we now have, before we had a ratio of lambdas, here we have a ratio of mu's, Lagrange multipliers. So with this formula, we can now get one equation to solve. So we're now going to substitute this into substitute this into the feasibility condition. And what do we get? Well, we sum over I. I'm just going to sum this. I want to sum the CTI. So I get UI prime minus 1 times this thing, U1 CT1 of ST. And now I have UI U1. That's going to have to equal I YTI ST. Okay, so what this tells me, so this is progress. Because I can use these two equations. I'll recycle notation. I'll recycle these stars and stars. So equations stars, equations star and star, we're going to stare at them. They determine, so what do they determine? They determine an allocation. They determine an allocation at a particular node for I equals 1 through I as functions. You know, how many equations do we have? We have I minus 1 equations here, and we have one equation here, if I'm counting right. Well, there's actually I equations, but one of them's trivial. So we have I minus 1 substantive equations here. One just says 1 is equal to 1. And we have this. So we have I equations in, so these are going to be functions of, what are these functions of? Well, we have I minus 1 plus 1 equations. And these are functions of, well, the right-hand side is just GDP. And then in addition, we have these multipliers, these ratios of multipliers. And we have 1 here, and we have I minus 1 non-trivial ones here, because mu1 over mu1. So we basically have I equations in I unknowns. Okay, and for each, look at this, for each T and ST. Remember, I keep thinking of Hicks and Arrow's idea that dynamics and uncertainty are just a special case of statics. Well, kind of true, but for each T and ST, we get I equations and I unknowns to solve for just a piece of the to solve for the allocation at that time and history. So for each T and ST, we're going to have to solve I equations and I unknowns, and there they are. By the way, you'll remember, to solve the planning problem, to get the allocation, we had to solve exactly the same number of equations at each history, at each time. It's kind of interesting. Okay. So let's say we've solved them. Suppose we have solved them. Question mark, have we finished finding a competitive equilibrium? Well, just have to go back and remind ourselves what a competitive equilibrium is. It's a competitive equilibrium is a feasible allocation. Well, we figured out we have an algorithm for solving that, and a price system. And we haven't computed the price system yet. So we're not quite done. So now let's go after the price system. Now must find the price system. Okay. Now, this step that we're going to do, there's some people who've made big contributions to economics, people like Alberto Bassin, Robert Lucas, Prescott. They made it because they made it because they're really smart and creative. But in addition, they were totally inside structures like this. And especially Lucas, he created a very famous model that we'll talk about if we have time, the Lucas asset pricing model. He took advantage of his intimate knowledge of the following step observation. So look what we've done. We've kind of proceeded recursively, kind of backed into it. In computing this equilibrium, we first went for the allocation, And we postponed solving for the price system. But now we're just going to kind of go back and say, now how we're scratching our head. How can we find the price system? Well, now we're going to go back here, and this equation, we're going to remember we had this equation, which was our rearranged first order condition with respect to CTIST for a particular individual, particular consumer. And if we stare at this, wow, look at it. Look at it. So what do we know here? What do we solve for here? What we have, solved for here is the allocation as functions of the aggregate endowment and the Lagrange multipliers. Okay, so here's our system. So we're going to need some more equations. So so these are the equations above, we had this system of equations star and star star. These were equations they were I equations they were I equations in I'm counting variables in CTIST, that was one, and in these ratios and multipliers. So that this was I equations. Okay, and we could solve them. We could solve them for consumption as a function of the multipliers. So now let's take the price system. So the price system is, we're going to get some additional, we're going to get one additional equation. We get one additional equation for each T and ST. Because if we know the CTIs, and we know the multipliers, then we can solve for QT. So essentially we have, basically what we've done now is we have I plus 1 equations in CT in the CTI in this one consumption in the ratio of the multipliers. I'm thinking out loud because this is good for me. And this. We want to solve them. Okay. Okay, so let's continue. This is a matter of seeing if Sargent can count. Okay, let's count equations. How many equations do we have here? Let's do the counting in black. This is going to be, there's going to be one of these equations for, like we said, there's going to be this is going to be this pair of equations, as we said before. This is going to be I equations in these variables, CTIST, and these variables for, we could think of it as for I being actually 1 through capital I. So actually we have I equations in how many variables? We have, well, there's I variables there, and there's I variables there. We can actually, it's going to turn out we can normalize one of these. We'll talk about that later. So we have I variables there and I variables there. And so we have I equations in 2I variables. So we're short of equations. We're short of equations. Okay, so we actually, what we said earlier, suppose we have solved them. Well, we can suppose that we've solved them, but we don't have enough equations to solve for the allocation. If we knew the allocation, we would know that it had to satisfy this equation. And it's kind of interesting. We get one, it would actually be one additional equation for each T and ST, and it would have, it's interesting, it would have a UI and a CI there. So we're not done. So in a particular, we need more equations. Oops. So we are not done. We need more equations. So we have not used all the equations that we have. So so what we have to do is we have to go back to the individual's problem. You know, I forgot to look at something that came from this problem. So there's a first order condition. And I've been working with that, but I haven't been working with something else. And that is now the Lagrange multipliers come into play. These Lagrange multipliers. I have not been working with minimization of this with respect to the MUIs. In particular, I haven't guaranteed that the budget constraint satisfied. And the budget constraint is the key thing that we have to add. So in particular, I'm going to add the budget constraint. So I'm going to add the budget constraint at equality. At equality, the budget constraints at equality to our system of equations. Okay, so here's what that looked like. It looked like summation QT. I'll write it this way: QTST. Was a sum over T. It's a sum over ST. QT0 CT I ST. That's my present value of consumption. Has to be less than or equal to summation T, summation ST, QT0. There's my price system. Y T I S T. That's the present value of my endowment. And I have, how many of these equations I have? I have an equation like this for I equals 1 through I. Okay. So what I have to, and I'm going to impose these at equality. I'm going to convert them to from inequalities to equalities because my agents like to consume. So now I'm going to call this, let's see, we have these numbered. I'm going to call this triple star. Okay, so what now I have, formally, now I in effect have, and I'm going to call this is, I'm going to call this twiddle. I'm going to call this twiddle because, yeah. Well, actually, let me do this. Call this triple, 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 4 stars. Okay, so now what I have is I have I equations here. I have one equation here. Okay. It's one equation in at a particular date. So here's what I'm doing. All the structure of these equations. I'm just attacking a particular. I'm looking for an allocation, and I'm just focusing on the component at TST. I'm just looking at that. So star, star, star. And triple star. I'm sorry. Let me make this more beautiful. Let me notice this. Star, 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 and involve only objects at TST. Star, star involves objects at all TST. So if I count equations and unknowns now, that's kind of an interesting thing to know as a start for analysis, because you kind of know whether you have enough. We're investigating, do we have enough restrictions to determine the things we have to determine, and it's going to turn out we do. Now we have I plus 1 equations here, and see here. Remember here we had I equations in 2 I variables, so we were vastly short. So we're seeking additional variables. Here, additional equations. Here we picked up 1 equation and 1 variable, so that was kind of a wash. But here, actually, if I do the following, if I take this, let's do this. I'm going to take this here. I'm going to sweep this in. I'm going to use this equation to take all of this stuff in the right way. And I'm going to substitute that into Q wherever it appears. See what I'm doing? So I'm going to eliminate Q just by doing that. So I've gotten this equation out of there, and I've gotten Q out of there. So now I've substituted out triple star. So this additional equation, remember I had I equations in 2 I variables. Well, now I've got my additional 2 I equation. These are I equations. So now I have 2I equations in 2I variables. Finally, okay. But it's kind of so I have to solve them simultaneously. And what do I have to, so here's the solution strategy. Solve star, star, star. And I'm going to put star, 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 star prime. That's the one I've substituted in. I've substituted in the QTs. I've eliminated the QTs. Solve these simultaneously. For what? For what? For, here's what I got to solve for. The CTIs and the mu i's over mu 1's for I equals 1 through I. So there's going to be 2I variables that I've solved for. And I've got to do that. I've got to do that. Well, now it's a mess because to do this, I have to do this for all t, for all st. I cannot do it period by period. So essentially, counting equations, now I'm up to like having infinite number of equations really quickly. And you can see how I got to that. Because as soon as I get to this equation, I've got to sum across all of these things. And I need to do that to get enough additional equations for I. So for the mu i's. Okay. So solving these all simultaneously is challenging. This strategy in principle could work. And I'm not done yet. Then use star, star, star to back out the Q's. For all T, for all ST. So we're computing a huge number of prices. Okay. Okay. So this is challenging. So let's pause here, and what I'm going to give you another a line of attack on solving these simultaneous equations, which is going to use something about the relationship between the planning problem and a competitive equilibrium. So that's what's going to be coming up next.